Assalamualaikum to all students. So far we already done on the diffusion through stagnant and equimolar counter diffusion for gas. I think we already gone through the equimolar counter diffusion for gas, diffusion through stagnant film for gas, and also we already touch on the diffusion plus convection for gas. Okay, next we will look into liquid. So liquid will be the same, so we will see how will be the equation for the equimolar counter diffusion for liquid, and also the diffusion through stagnant film for liquid. Okay, for liquid it is a little bit different compared to gas. Okay, so diffusion of solute in liquid, this is example of the process that involve of diffusion of solute in liquid. For example, we have liquid extraction. This will be teach later in chapter 4. Okay, so liquid extraction is example of diffusion of solute in liquid. Okay, so gas absorption and oxygenation of reverse by the air. Okay, so liquid, the molecule arrangement is packed together, and it is actually more closely than gases. So the density and the resistance to diffusion in liquid is much greater than gas. For example, if I can draw for you, this is gas. Okay, for example, this is gas, the molecule arrangement in gas. So this is molecule arrangement in liquid. So you will notice that liquid, the arrangement is much more close than gas. Okay, so when the molecule arrangement is quite close and packed together compared to gases, so the resistance to diffusion is greater, okay, compared to gas. And when the resistance is greater, the flux is lower. Okay, flux is when we put, for example, here when we put dye in the liquid, the flux of the dye, okay, flux or the rate of diffusion for the dye to diffuse in the water is actually lower than in the gas. Okay, so the difference of diffusion in gases with diffusion in liquid, so there are the one difference between diffusion in gas and diffusion in liquid. So in diffusion in liquid is often dependent on the concentration. I think I already mentioned before. So liquid will much more depend on concentration. Okay, so for example, if if you can still remember for the formula diffusion through stagnant film, for gas we will change the concentration into P over RT. So in gases, the most important parameter or the limiting parameter for diffusion in gases is the pressure, temperature, and also the gas constant. However, in liquid, it will much more depend on the concentration. So we will see later all the formula or the equation will have concentration term. Okay, so this is example. Okay, for example, I think this is one of the example of liquid extraction. Okay, so what happened in liquid extraction? So we have solvent. Okay, this is solvent, and we have a feed solution. Okay, so the feed solution will contain solute A and solute B. Okay, two types of solute. So the these two component or these two solvent and the feed solution will be mixed together. Okay, will be mixed together, mixing, we stir, and there will be it will undergo phase separation. Okay, what will happen is the solvent will only attract or will only extract the solute A only. Okay, there will be some of the solid B, but not much. Okay, most of the solid A will be extracted by solvent. Okay, so the feed solution here will be remain or will only left with the solid B. Okay, so the diffusion of solid A from the feed solution to the solvent, that we call it as a diffusion, and it involves flux. Okay, so we will calculate the flux. So this is liquid extraction, whereas the solvent only extract, or it will only extract one type of solute. Okay, only favorable to one type of solute. So the diffusion of solute A from the feed, it will diffuse through the solvent. So the diffusion is what will be calculated here. Okay, so this is another example of gas absorption. Okay, absorption. So just now we see the example on liquid extraction. So this time, so we will see on the gas absorption. So what is gas absorption? Okay, for example, I have gas here. Okay, this gas contains solid A and solid B. Okay, so the objective of the gas absorption is actually to remove one of these solute. Okay, let's say I want to remove solid A, and solid A can only be extracted by using solvent, one type of solvent. Okay, for example, solvent C. Okay, so the solvent will be in liquid form. Okay, so this will be the solvent. So this is the gas absorption tower. Okay, so the gas that consists of these two solute will enter the tower from downwards. Okay, so it will be purged in, and on the same time, so the liquid, which is the solvent, okay, which is favorable to extract solid A, will be pumped in from the top of the tower. So when the liquid and the gas mix here, this is what we call packing. Okay, later on I will teach you on gas absorption chapter. So when they mix, the solvent and the gas mix, so the solute A will diffuse from the gas and it will enter the solvent. Okay, so the solvent will goes downwards, the gas will goes upward, so they will in contact, and the solvent will attract the solute A. So the solute A and the solvent will left the tower. So the liquid, the solvent here, for example, if I say solvent C, it will have the solute A. Okay, so the gas out here will only have solute B. Okay, because the solute A already being extracted by the solvent. So the diffusion of A into the solvent is what we call the diffusion in liquid. Okay, so this is how the diagram, the detailed diagram. Okay, so the on how the diffusion of the solute A, for example, SO2 is the solute A and H2SO3 is the solute B. Okay, so the solute A will diffuse into the liquid. Okay, for example, so the diffusion is what we want to calculate. Okay, which is the diffusion flux of solute A from gas to liquid. Liquid is the solvent. Okay, so let's see equimolar counter diffusion in liquid. So in liquid we will use the general term. I think you can still remember this term. This is from the we derive from the diffusion of gas plus convection. So this will be the general equation. Okay, So equimolar counter diffusion in liquid. So when we have counter diffusion in liquid, for example, I have okay, I have here is the solvent in, and this is the gas in. So the gas will have solute A and B. Okay, the gas will left with solute B only, and this solvent will left with solvent plus with solute A. Okay, so when we have the counter diffusion in liquid, the flux of A, okay, for example, the flux of A is equal to negative flux of B. Okay, so I think this is the same concept as the gases. So when we have Na plus Nb here, Na is equal to negative Nb if we replace here. So negative Nb plus Nb will be 0. So this term will be 0. So it will left only with this term, which is the fixed law. Okay, so for equimolar counter diffusion in liquid, we will use this equation, and this equation will be further integrate, and we will get this equation. Okay, so DAB CA1 minus CA2 over Z2 minus Z1. Okay, so this equation can also be written as a mole fraction. So when we if you want to write in mole fraction x term, so we will put concentration average here. Okay, so for x in the flux of A in equimolar counter diffusion, so from C, if the equation give you the mole fraction, you can use this equation. Okay, so but you need to have C average here. Okay, so for C average, this is the equation for C average. So C average is equal to density divided by the molecular weight. Okay, so this is the density, this is molecular weight. So the average of the density over molecular weight is the concentration average, and it can also be expressed in density 1 plus density 2 over m1 over m2 divided by 2. Okay, so this is the formula for C average. Okay, when you calculate the C average using this formula, and you can insert the value into this equation, and you can solve for the flux. Okay, so this is in terms of the molar fraction. If you are given concentration, you can use this equation. Okay, so you can see here diffusion in liquid often quite dependent on the concentration. You can see from the equation itself, because of we have the element of concentration here. So yes, in liquid the concentration term is very important. Okay, so we are done for equimolar counter diffusion for liquid, and next we will see how will be the equation of diffusion through stagnant film in liquid. Okay, so the diffusion through stagnant film, non-diffusing B in liquid, I think this is very straightforward for the equation. Okay, for example, we have propionic acid and we have water. So the propionic acid in water, we contact with toluene. Okay, so this is like, for example, the liquid expression. So the toluene will only extract the propionic acid, so the water will not diffuse to the toluene. Okay, so the propionic acid will pass through the water in order to diffuse into the toluene. So the toluene will extract the propionic acid. So the toluene water is a barrier to diffusion of B, and NB is 0. So for example, here I have okay, here is I have the toluene. Okay, here I have propionic acid, and I have water. Okay, so when in contact in the tower, so toluene will left with toluene plus the propionic acid. So water will left here alone. Okay, so because the toluene only extract the propionic acid. In order for the propionic to be diffused to the toluene, so it will need to gone through or pass through the water, so the water barrier. Okay, so and water will not dissolve into the toluene. Okay, so the flux of B, which is the water, this is component B, this is component A, so the flux for B is considered 0 because it doesn't diffuse into the toluene. Okay, so the NB will be 0. So it is the same situation as the gas. Okay, diffusion through stagnant film, non-diffusion B in gas. So if you can still remember, so we have, this is the formula for diffusion through stagnant film in gases. These two formulas, can you still remember? Okay, so for diffusion through stagnant film in liquid, so we only change the equation into molar fraction and concentration terms. Okay, so for example, in order to change, so we P over RT will be changed to C average is equal to P over RT. I think you can still remember this from the diffusion in gases. Okay, so the P over RT will be changed into C average. That's why we have C average here. Okay, so the P here will be replaced with mole concentration, and PA2 will be changed to XA2 here. Okay, so we will have this equation, this direct transformation of the equation from gas to liquid. The same goes for here. So we have another example, if you can still remember, by using PBM. Okay, so we only change the P over RT into C average. Okay, C average here, and PA1, PA2 into XA1, XA2, and PBM into the XBM. It is more or less like the C. Okay, so for the XBM, the equation, it will be XB2 minus XB1 divided by ln B XB2 over XB1. Okay, this XBM is also equal to 1 if we have a dilute solution. So if in the question mentioning that the solution is dilute, so XBM is equal to 1. Okay, so for C average, I think the formula is still the same like before this one. Okay, so the C average is equal to density P1 rho 1 over M1 molecular weight plus rho 2 over M2 is divided by 2. Okay, so this is for C average. So for molecular diffusion of liquid, so we have for equimolar counter diffusion, so we will use the C average, this one, DAB, CA1 minus CA2. So this is from the Fick's law. Okay, so if we want to change in X term, molar fraction, so we will add the C average term here. Okay, so there will be two equations for molecular diffusion in liquid. So for diffusion through stagnant non-diffusion B, which is Na, is equal to DAB over Z2 minus Z1 XBM. Remember XBM. Okay, you can use for XBM, you can use, if you use concentration here, so you don't have to put C average. Okay, if you want to use molar fraction here, so you need to put C average here. Okay, so another term is on ln, this is on X term. Okay, a molar fraction term. So in molar fraction, if you do not want to calculate for XBM, you have to put ln here. Okay, so for X term, you need to have C average. Okay, so these three equations are the three different equations. So you can use either one based on the information given in the question. Okay, so depends. If the concentration 1 and concentration 2 are given, you can straight away use this equation. But if you don't have the CA1 and CA2, you can use C average. So C average, you need to have row 1 and molecular weight. Okay, so you need also to calculate the XBM. Okay, so it all depends on the question and the information given. Okay, so we are done on diffusion to stagnant film and equimolar counter diffusion in gas and liquid. Okay, next we will see how the diffusion flux in solid. Okay, so if we compare solid, liquid and gases, solid, as I mentioned before, the diffusion in liquid much more slower than gases. So the solid flux, the diffusion in solid will be much slower than liquid and gases. Okay, I think you can guess why, because of the molecular arrangement. Okay, so the solid will be packed together. So this is example of diffusion in solid. So the diffusion of phosphorus and boron into silicon, the diffusion of nitrogen or hydrogen in the rubber. Okay, diffusion of water into foodstuff. So foodstuff is usually in solid, or the reaction process or diffusion into the catalyst. So the catalyst that we use usually in solid. Okay, so the diffusion in solid is actually exists. Okay, so there are two types of diffusion in solid. So diffusion in solid usually will follow the Fick's law. Okay, the ideal case. Okay, it will not depend on the actual structure of the solid. And number two, diffusion in porous solid, where the actual structure and void are important. So there are two types of diffusion in solid, which is using following Fick's law. It doesn't depend on structure of the solid. And number two, we have porous solid, where the diffusion will follow the structure of the solid. Okay, so when we have diffusion in solid, which do not depend on the actual structure, it will use the general equation here. Okay, so for the diffusion which does not depend on the actual structure of the solid, okay, usually the terms at the back here is small. The value is small and negligible, so this will be neglect, and the term will left only with this equation. Okay, so this equation will be is actually the Fick's law equation. Okay, you can use the dXA and also dCA. You can refer this one at the earlier slide. Okay, this were on the Fick's law. Okay, so this, when we want to, if we integrate the terms, so we will get this equation. Okay, so this is referring to the Fick's law. Okay, so but for solid, the calculation for the concentration is will be the different. Okay, so here the concentration here will be calculated using this formula, which is solubility times with the partial pressure of A divided by 22.414. Okay, so if you calculate, if you want to calculate the flux of diffusion A, for example, if you have gas A in solid, so you the concentration you need to calculate by using this formula. Okay, the solubility of the concentration Ca will depends on the solubility of the gas in a solid. Okay, so you can use this equation to calculate the concentration Ca, and you, after you get the value, you put into this equation and you get the flux. Okay, so for gas, I think that's all. For gas, the equation is following the Fick's law. Only the calculation for the Ca, you have to depends on the solubility, and you can use this equation. Okay, that's all. Thank you.